Waveguide junctions, directional couplers, part 1, series on microwave engineering, lecture number 1.18. Directional couplers are passive devices. They are linear devices. They are microwave devices. They fall in the category of junctions. Hence, they are capable of dividing a power stream into two or more power streams, and also they are capable of combining two or more power streams into one. But primarily, directional couplers are used to divide power, not to combine power streams. There is one basic or fundamental difference between directional couplers and other microwave junctions like E plane T, H plane T, EH plane T. In T junctions, the power division is always half-half. The input power is divided into two equal halves. But in directional coupler, the division can be as per our requirement. 1/10 of input power can be diverted, 1/100th of input power can be diverted, 1,000th of power can be diverted, even half of the power can also be diverted. According to the requirement, one can divert, separate the power with the help of directional couplers. These are widely used in microwave industry and in microwave research. In the present session, the focus is on introduction to directional couplers, their port naming, their port numbering, symbol of directional couplers, the properties of directional coupler, the structural features of the directional couplers. Apart from these aspects, several other interesting aspects of directional couplers are also considered and described here. Now, let us move into the core session. Directional coupler, or DC in short, is a reciprocal lossless matched 4-port network with a facility to sample portions of the forward and reverse traveling waves on a line at two of its ports separately. This statement gives almost complete information, total information pertaining to what is directional coupler. What does it do? It says it is a 4-port device. All ports are matched to the device. It is a lossless network. It is a reciprocal. It is associated with a facility to sample forward wave and reverse traveling waves on a line separately. These sampled waves appear at two of its ports separately. It is also called symmetric coupler and quadrature type hybrid. 4 ports are there. Numbering of the ports is an important aspect as far as microwave junctions are concerned. While numbering the ports, usually it is done either clockwise or in anti-clockwise manner. Sometimes even Z manner is also followed. Ports, they have names. Any one of the 4 ports of the device can be connected to the signal source, and then it is called input port and it is numbered as 1. The port opposite to the input port is called through port or output port. The port which is just below the input port is called decoupled port, and the remaining port is coupled port. So 4 ports. The port where input is connected is input port, where source is connected is input port. Opposite to input port is through port or output port. Port just below input port is decoupled port, and the remaining port is coupled port. The guide which has input and output ports is called main or primary guide, and second one is called auxiliary or secondary guide, the one which has decoupled and coupled ports. The structure of directional coupler consists of two pieces of rectangular waveguides with a connection or coupling between them. Each piece has two openings. The piece which has input and output ports, that piece is called main or primary guide, whereas the second one is called auxiliary or secondary guide. Here in this slide, a good amount of information pertaining to directional couplers is given through four figures: A, B, C, D. In A, symbol of the directional coupler is given along with port numbering. Left hand side, top one, that port is given number 1. Usually input port is given 1. The port below input port, it is given number 2. Port opposite to 2 is given 3. Above port 3 is given 4. Hence 4 is the output port. 1 is input port, 2 is decoupled port, 3 is coupled port, 4 is output port. The numbering is given in anti-clockwise manner. In B is given a simple form of directional coupler constructed with two pieces of rectangular waveguides. There is a common wall. In the common wall, one can notice there exist two holes. The distance between these two holes is set equal to odd number of quarter wave lengths. The size of the holes, the shape of the holes decide the amount of power that is diverted, amount of power that is separated from the main flow. The functioning is like this. Source is connected at port 1. Its output flows towards port 4. A fraction, it may be a small fraction of this power flow from 1 to 4, it is diverted to port 3. The amount that is diverted depends upon the size, shape of the holes. Under ideal working conditions, no power appears at port 2. In C is shown a directional coupler, but here it has 4 holes. The structure can be seen somewhat complicated when compared to the 2-hole directional coupler. But the coupler that is depicted in C, it gives better performance in terms of directivity and also in terms of broadband characteristics. In D is shown another directional coupler, a sophisticated one. Here, a waveguide is standing on its narrow wall. Over another narrow wall, one can find another piece of rectangular waveguide lying with its broader wall in contact with the narrow wall. Bottom one is primary guide, whereas the upper one is secondary guide. Here also one can notice the existence of two slots, two holes with a distance of lambda g by 4 between them. These are for the sake of coupling, power coupling from primary guide to secondary guide. This is Springer coupler. The coupler that is shown in B is quite crude, but it is useful in understanding the functioning of directional couplers. Whereas D, coupler shown in D is a sophisticated one with a decent performance characteristic. Now we try to understand the properties of directional couplers. With respect to the port designation given in the symbol in the previous slide, in an ideal DC, all the 4 ports are perfectly matched to the junction. Ports 1 and 2 are perfectly isolated. Similarly, ports 3 and 4 are also isolated. 1 is input port, 2 is decoupled port. There exists perfect isolation. Of course, it is in ideal case. In case of ideal directional coupler, perfect isolation exists between 1 and 2, between 3 and 4 too. In practical couplers, however, the isolation is not perfect. And as a consequence, a portion may be very small of the input appears at the isolated port. A portion of the wave traveling from port 1 to 4. 1 is input port, 4 is output port. A portion of the wave from 1 to 4 is coupled to port 3, but not to port 2. Similarly, a portion of the wave traveling from port 1 is coupled to port 2, but not to port 3. So input is given at port 1, it travels to port 4. If port 4 is match terminated, then entire wave gets absorbed there. No reflection happens. Otherwise, a part of the wave reached port 4 gets reflected. Now we have two waves over the line in between 1 and 4. The wave from 1 to 4, a part of it appears at port 3. So it is like this. The wave from 4 to 1, a part of it appears at port 2, decoupled port. In transmission line theory terminology, wave from 1 to 4 is forward wave or incident wave. Wave from 4 to 1 is reverse wave or reflected wave. So in directional coupler, we have the facility of forward wave being sampled, reverse wave being sampled separately, individually, and the sampled outputs appear at two different ports separately. Some more properties. A portion of the wave traveling from the port 2 to 3 is coupled to port 4 but not to port 1. Similarly, a portion of the wave traveling from port 3 to is coupled to port 1 but not to port 4. The coupling between ports 1 and 3 is the same as that between ports 2 and 4. The amount of sampling is same. It implies the amount the forward wave is sampled is equal to the amount the reverse wave gets sampled. If 1/10 of forward wave is separated, diverted, same 1/10 of reverse wave also get separated or diverted. Similarly, the coupling between ports 1 and 4 is same as that between ports 2 and 3. The outputs are always at phase quadrature, exhibiting a phase difference of 90 degrees. For this reason, directional couplers are often called quadrature type hybrids. What he says is, this is directional coupler. Here input is given. Most of the input appears at port 4, output port. A small portion of this wave 1 to 4, it appears at a coupled port 3. Under ideal conditions, no output at port 2, decoupled port. Now, input is given at port 1, output is majority at 4, usually a small portion at 3. So, 4 and 3, they can be considered as the ports or output ports, outputs. The outputs at ports 4 and 3, they have certain constant phase difference equal to 90 degrees. It is always 90 degrees. Here also directional couplers differ from T-junctions. In E-plane T, the outputs are with a phase difference of 180 degrees. In H-plane T's, outputs are in phase. In EH-plane T's, the outputs can be at a phase difference of 0 or 180 degrees. But in case of directional couplers, it is always 90 degrees. Here is shown the structural details of waveguide directional couplers. In A, the directional coupler is said to be of in H-plane style. In B, the directional coupler is said to be in E-plane style. One can see pieces of rectangular waveguides go into the structure of the directional coupler. Notice in both the cases, bends are used as auxiliary guide or secondary guide. Straight rectangular waveguide piece is used as main guide, whereas bend, H-bend is used as auxiliary guide in case of H-plane style directional coupler, and E-bend is used as auxiliary guide in case of E-plane style directional coupler. The decoupled port is match terminated in both the cases. Port 2 is not available. Now another class, another variety of directional couplers are introduced. They play certain important role, significant role in research and measurements in microwave engineering. They are Bethe-Hole directional couplers. These are available in two versions. One version is parallel guide coupler and another version is skewed guide coupler. In parallel guide coupler version, the two guides are parallel, one lying over the broad wall of the other with a small hole aperture in the common broad wall. The offset S from the side wall of the guide controls the coupling. In the skewed guide coupler version, one guide is over the other at an angle theta, which controls the amplitude of the coupled waves. The geometry of the skewed Bethe-Hole coupler is often a disadvantage in terms of fabrication and application. The structural details of Bethe-Hole directional couplers are illustrated in this diagram. Notice a common hole or a hole in the common wall. The distance of the hole from the side wall determines amount of coupling. Directional couplers can be divided into single hole couplers and multi-hole couplers. They can also be classified into forward couplers and reverse or backward coupler. Bethe-Hole coupler, it belongs to single hole variety falling in the category of reverse or backward wave couplers. The origins of these couplers lie in a paper published by H.A. Bethe in 1942. It is a starking difference as far as port locations are concerned between forward couplers and reverse couplers. Coupled and decoupled ports in backward couplers, they interchange their locations with respect to their positions in forward coupler. Port near to input port is coupled port and port opposite to input port, of course it is in both the varieties, through port and port which is opposite to coupled port is isolated port. Here is shown Bethe-Hole directional couplers. It's two varieties. In A, parallel guide variety, in B, skewed guide variety. One can see. Notice in both the cases, in A and B, input port and coupled port, they are near to each other. In case of forward couplers, input port and isolated port, these two are near to each other. But as Bethe-Hole is reverse coupler, input port, coupled port are near to each other. And one can also notice against input port, it is through port that exists. It is not isolated, small correction, it is through. Against coupled port, it is not through port, it is isolated. In B, one can notice against input port, through port is there, against coupled port, how isolated. In both the cases, in both A and B, through port and isolated port, they are near to each other. Now, a few points regarding the functioning of Bethe-Hole directional coupler. In this coupler, one waveguide is coupled to another through a single small hole in the common broad wall between the two guides. According to small aperture coupling theory, an aperture can be replaced with an equivalent sources consisting of electric and magnetic dipole moments. The normal electric dipole moment and the axial magnetic dipole moment radiate with even symmetry in the coupled guide, while the transverse magnetic dipole moment radiates with odd symmetry. By adjusting the relative strengths of these two equivalent sources, the radiation in the direction of the isolated port can be nullified, while enhancing the radiation in the direction of the coupled port. In case of parallel guide coupler version, the coupling is controlled by the aperture offset S from the side wall, whereas the angle theta between the guides controls the coupling in case of skewed waveguide coupler. Also, both coupler designs operate properly only at the designated frequency. At the frequency where they are designed, deviation from this frequency will alter the coupling level and also the directivity. These are some of the things which I want to share with you with respect to directional coupler. The device, microwave junction, directional coupler is introduced. Its characteristics, its structural details, different types of these devices. and several other interesting aspects are also introduced, explained. Hope you have fruitful, successful, beautiful, wonderful, enriching learning experience. See you soon. Bye bye.